Welcome to the DAC chapter of the HT32 MCU basic tutorial. There are 5 chapters in this tutorial, including the DAC Introduction, the DAC Architecture, the DAC Mode, the DAC Function, and finally the relevant settings and applications. DAC Introduction. Let's first understand what DAC is. DAC is an abbreviation for Digital to Analog Converter. A digital signal is binary data composed of a series of 0 and 1. The DAC is used to convert these digital values into the corresponding analog voltage. Let's take a simple example. The digital data on the left are written to the DAC in sequence, and the DAC will generate different analog voltages based on different digital data. The analog voltage signal is a sine wave with an amplitude of 3.3 volt. DAC Architecture. Then let's look at the DAC architecture. We can start where the digital data is written, which is the DAC XDHR register. First, we need to write the digital data in the DAC XDHR register. Whether the data is 8-bit or 12-bit data depends on the DAC resolution setting. Then the digital data will be processed by control logic. According to the configured synchronous or asynchronous mode, the control logic will transfer the data into the correct location of the DAC XDOR register to complete the preparation of the digital data. Before preparing the digital data, we first must set the reference voltage source. We can configure either an internal reference voltage VREF or an external voltage VDDA as reference voltage source by using the VREF SEL control bit. The choice of reference voltage is very important because it directly affects the DAC analog output voltage range. Then the DAC starts a digital to analog conversion and generates the corresponding analog voltage based on the digital data value and the reference voltage, and then decide whether to output or not according to the DAC N-bit setting. After the conversion is completed, the analog signal can be selected whether to pass through the buffer or not. The buffer is used to enhance the driving capability of the analog signal and improve the signal stability and interference immunity. Finally, an analog signal with a conversion rate of up to 500 kilosamples per second can be observed at the DAC I/O output pin. DAC Mode. In order to understand the DAC synchronous and asynchronous modes more clearly, let's illustrate with a concrete example. We first start with the asynchronous mode. First write the digital data 0 into the DAC 0 DHR register. The data is transferred into the DAC 0 DOR register through control logic and the DAC conversion is performed. After the conversion is completed, DAC 0 OUT will generate a corresponding analog signal. Then write the digital data 1 into the DAC 1 DHR register. The data is transferred into the DAC 1 DOR register through control logic and the DAC conversion is performed. After the conversion is completed, DAC 1 OUT will generate an analog signal. In this process, the DAC 0 OUT signal is generated first and then the DAC 1 OUT signal is generated. There is a time difference between these two signals. If we want DAC 0 OUT to generate a signal at the same time as the DAC 1 OUT, we need to use the synchronization mode mentioned below. We will combine a data 0 and a data 1 and write them into the DAC 0 DHR register. The data will be split into the DAC 0 DOR and DAC 1 DOR registers by control logic. And the DAC conversion is performed simultaneously, and after completion, the DAC 0 OUT and DAC 1 OUT will generate analog signals simultaneously. From the above examples, we can clearly understand the difference between asynchronous mode and synchronous mode. In the asynchronous mode, each DAC channel operates independently. The generation time of analog signals varies depending on the order in which the data is written into each channel. In the synchronous mode, multiple DAC channels operate simultaneously and each channel generates an analog signal simultaneously. There are 4 combinations of asynchronous or synchronous mode and 12-bit or 8-bit data format. Each combination has a different data processing method, which is organized as follows. Let's first introduce the combination of asynchronous mode and 12-bit data format. The 12-bit data can be written directly to the DAC XDHR register and the data remains unchanged after transferring into the DAC XDOR register. The combination of asynchronous mode and 8-bit data format. The 8-bit data can be written directly to the DAC XDHR register, and the data will be shifted left by 4 bits and then transferred into the DAC XDOR register. The combination of synchronous mode and 12-bit data format. The 2-channel data is first combined into 32-bit data and written into the DAC 0 DHR register. The higher 16-bit is channel 0 data, and the lower 16-bit is channel 1 data. The 12-bit data of each channel will be transferred into the corresponding DAC 0 DOR or DAC 1 DOR registers. The combination of synchronous mode and 8-bit data format. The 2-channel data is combined into 16-bit data and written into the DAC 0 DHR register. The higher 8-bit is channel 0 data, and the lower 8-bit is channel 1 data. The data of each channel will be shifted left by 4 bits and then transferred into the corresponding DAC 0 DOR or DAC 1 DOR registers. DAC function. The DAC output voltage is calculated as follows. For the 12-bit digital data format, the output voltage is a 12-bit digital value multiplied by the reference voltage and divided by 4095. For example, input a value, half of 4096, 2048, and the reference voltage is 3.3 volt, thus the output voltage is half of the reference voltage, 1.650 volt. While for 8-bit digital data format, the output voltage is an 8-bit digital value multiplied by the reference voltage and divided by 255. For example, input a value, half of 256, 128, and the reference voltage is 3.3 volt, thus the output voltage is 1.656 volt. It can be observed that the output voltage has an error of 6 mV for the 8-bit data format due to the lower resolution. The DAC output buffer is disabled by default, as shown below, DON is 1 and DBON is 0. If we need to enhance the driving capability of analog signals, we can enable the output buffer. The first step. Set DON to 0. Set DBON to 1. It is noted that DON and DBON cannot be set at the same time. DAC Settings and Applications. The example program is from the DAC example SYSC 12-bit CH of the HT32 FW lib. First configure the DAC. Enable the DAC clock. Configure the I/O pin as the DAC channel 0 and channel 1 output. Configure as the synchronous mode. Configure VDDA to the channel 0 reference voltage, and configure as the 12-bit digital data format, and enable the DAC output buffer. Configure VDDA to the channel 1 reference voltage and enable the DAC output buffer. After completing the DAC settings, enable the DAC channel 0 and channel 1. At this time the data has not been set, therefore the converted voltage is 0. Finally, write a digital data, chconf data all, and further analyze the content of chconf data all. First, define the output voltage of the two channels as 1650 mV, which can be calculated by the following formula. Calculate the digital data and finally combine the data of channel 0 and channel 1 into chconf data all. After the data is written, it will be found that both DAC channel 0 and channel 1 output 1650 mV at the same time. At the end of the tutorial, this is a list of DAC APIs. The content includes the DAC driver API provided by the HT32 standard firmware library, as well as a description and a DAC register list. Holtec has a professional service team to assist in the development, design, and after-sales service. Welcome to contact our business unit for more detailed product information and consulting services.